In this lecture, we will discuss the fundamental principles of radionuclide-based diagnostic tools. SPECT and PET are two commonly used radionuclide diagnostic tools. Single photon emission computed tomography is known as SPECT. Radionuclides that emit gamma rays are used in this apparatus. The positron emission tomography is represented by PET. In contrast to SPECT, this device employs positron-emitting radionuclides. There will be two parts to this lecture. The first section covers the methods that generate artificial radionuclides. The fundamental concepts of SPECT and PET will be discussed in the second section. This table shows the methods to generate radionuclide. We can use a cyclotron, nuclear reactor, and radionuclide generator to obtain radionuclide. We will discuss these methods in detail thereafter. In cyclotron, we will use bombarding particles to make nuclear reaction of the certain material. As a bombarding particle, we can use proton, deuteron, triton, and other particles. And nuclear reactor, there are abundant of neutron, and we can put some material into the reactor, and then the material capture the neutron to become the radionuclide. In the cyclotron, we can obtain generally a positron emission radionuclide, and in the nuclear reactor, we can obtain the electron emission radionuclide, and a radionuclide generator, we can obtain some special kinds of radionuclides, these kinds of radionuclides. And you can see here radionuclides for nuclear medicine using cyclotron and nuclear reactor. Let's first see the artificial radionuclide production in a nuclear fission reactor. Nuclear fission divides the uranium-235 nucleus into two nuclei. This fission also emits an average of 2.4 neutrons per fission. Furthermore, each fission releases 195 million electron volt of energy. This energy is the nucleus binding energy. The binding energy between nucleons is released when a nucleus is divided up. This released energy is used by nuclear power plants to produce hot water vapor, which is then used to rotate turbines and generate electricity. 1 million watt of heat energy can be produced from 1 gram of nuclear fuel. We can produce around 1/3 of a million watt of power with 1 gram of nuclear fuel if 1/3 of the heat energy is transfer to electric energy. So the efficiency of the nuclear power plant is about 1/3. The fission of uranium-235 produces a large number of byproduct radionuclides. Radionuclides with an atomic number of 30 and 66 are generated in this process. So here we have two peaks around 66, the peak position, and here around 30, and the highest yields can be obtained in the nuclear fission reactor. So this figure shows byproduct radionuclides produced by uranium-235 fission in a nuclear reactor. Radionuclides are created by three types of nuclear reactions that take place in a nuclear reactor. The first is neutron capture, which is expressed by the reaction of this expression. The second one is nuclear decay, which is followed by neutron capture. The third one is fission, which is already shown in the figure. Neutron capture is the most common method for producing radionuclides in a reactor. The target material is just inserted into a reactor in neutron capture. The neutrons released by nuclear fission, such as that of uranium-235, are then captured by target material. As a result, neutron capture is simple and a high-yielding method. However, chemically eliminating impurities and thus obtaining pure radionuclide is impossible in this method. As a consequence, in order to obtain pure radionuclides, we must use as pure a target material as possible. Neutron capture in a reactor yields typical radionuclides such as molybdenum, chromium, and strontium. After neutron capture, some nuclides decay into final radionuclides. Iodine-131 and iodine-125 are two well-known examples. The nuclide xenon decays to iodine-125 by electron capture, or beta-minus decay after xenon-125 is neutron captured via this reaction process. The radionuclides created by this method, unlike neutron capture, can be chemically separated, allowing for the production of pure radionuclides. This table shows the radionuclides produced by neutron capture in a nuclear reactor. Here, target material is molybdenum. Molybdenum capture the neutron to become molybdenum-99, which is a radionuclide. And iodine-131 can be obtained from this reaction. Here, after neutron capture, the iodine-131 is decaying, and here also iodine-125. We can obtain iodine-125 from the target material xenon. Xenon is captured by electron. Xenon captured electron and become xenon-125 and is decaying and finally you can get iodine 125. So these radionuclides can be obtained in a nuclear reactor by using the neutron capture. Now let's see the generation of artificial radionuclides using a cyclotron. For the production of radionuclides, the cyclotron is the most commonly used particle accelerator. It was developed for the first time in 1930. Around 100 cyclotron machines are in use around the world. A particle accelerated by a cyclotron has an energy of 3 to 700 million electron volt. The basic principle of cyclotron's operation is depicted schematically in the figure here. The D structure is the most significant portion of a cyclotron. Two D-shaped structures stand in front of each other. The inside of these has an empty space where particles are accelerated. So inside these, the vacuum is maintained. So here we have two Ds which face each other. Between two Ds there is some gap. Let's have a look at how particles are accelerated. Ions are first produced using an ion generator. The ions are then injected into the space between the Ds. Here. So ions are generated and ions are injected into the space between the two Ds. A negative voltage is applied to a D to attract these ions, say protons, toward it. So the ions here, protons, if we put the negative voltage here in this D, then proton is attracted into this D. These are subjected to a high frequency or alternating voltage. So we can put the high voltage alternating voltage between two Ds. As a result, the polarity of the voltage applied to Ds alternates with the applied alternating voltage frequency. When protons enter a D, they are no longer aware of voltage difference. So proton is entering to this D. The protons move in a circular motion through the center of D due to the magnetic field applied perpendicular to the D's surface. So magnetic field is applied perpendicular to the D surface. Then the protons to the circular motion inside D. The protons escaping from 1D enter the gap between the two Ds after making a semicircular motion inside it. So protons here semicircular motion and enter the gap between two Ds. Okay. The polarity of the voltage applied to the other D switches from positive to negative at that time. So at this moment, the polarity of the field applied to this changed, right? So it was a positive, but now here negative and positive here. Then proton is attracted to this D and enter inside this D and to the circular motion. Okay. As a result, the protons are drawn to the inside of that D and begin to move in circular motion once more. Okay. Thus, it is critical to match the timing of changing the polarity of this voltage to that of protons entering the gap between the Ds for continuous proton acceleration. So we have to match the time of changing polarity for the proton to accelerate by this high voltage. When protons cross the gap between the Ds, they gain an energy of EV plus EV. As the protons go from one D to the next, the radius of the circular motion increases, as shown here. The Lorentz force of EBB is exerted on protons in a magnetic field B. This Lorentz force should be equal to the centrifugal force in a circular motion. As a result, we have this relationship, and the proton's angular velocity is given as this expression using above equation and the relation of omega equal velocity divided by radius. The angular velocity of the protons is independent of their velocity and the radius of the circular motion according to this equation. For the successive acceleration of the protons, we knew that the frequency of the alternating voltage had to match the angular velocity of the protons. As stated in this equation, the proton's angular velocity is independent of their radius. As a result, even as the radius of the circular motion of the protons increases, we do not need to change the frequency of the alternating voltage. In other words, regardless of radius of circular motion, the protons arrive at the gap between the two Ds exactly at the same time when the polarity of the voltage changes, even though the frequency of the alternating voltage remains constant. So we don't have to change the frequency of alternating voltage every time. The protons inside these are accelerated by the alternating voltage and emerges from the exit. After that, high-energy protons are fired towards the target material placed at the exit. Inside target material, this bombardment causes a nuclear reaction, so you can have the radionuclide. Besides protons, we can use deuterons, alpha particles, and other accelerating particles can be used. This table shows a typical radionuclides produced by a cyclotron. Here we can obtain fluorine 18 by using the target material neon. Neon is bombarded by deuteron. to become fluorine 18. Okay. And its half-life is about 2 hours. This fluorine is selectively used in the PET. Oxygen 15 can be obtained by bombarding nitrogen by deuteron. Its half-life is just 2 minutes. Cobalt 57 is obtained by using iron as a target material, and bombarding particle is deuteron, so we can have cobalt 57. Iodine 131, we can use xenon as a target gas, and this xenon is bombarded by proton and then becomes CS123, and the CS123 is decaying to become the iodine 123. We can also obtain iodine 131 using iodine 127 bombarded by proton. Then this can be become the xenon 123, and xenon 123 is decaying to become the iodine 123. Gallium also can be obtained by using zinc as target material, and zinc is bombarded by proton, become gallium 67. And indium 111 can be obtained by using the cadmium 111 as target material, and this cadmium is bombarded by proton to become the indium 111. And this column shows the half-life of these radionuclides. Now let's see the production of artificial radionuclides by radionuclide generators. The radionuclide generator is used to produce radionuclides with a short half-life. The decay of a parent radionuclide with a long half-life produces a daughter radionuclide with a short half-life. The daughter radionuclide is separated from the parent radionuclide chemically or physically. After the separation of the daughter radionuclide, the decay of the parent radionuclide continues to produce the daughter radionuclide. As a result, we can separate the daughter radionuclide at regular intervals until a proper yield of daughter radionuclide from the parent radionuclide is no longer possible. The radionuclide TC99M is most often utilized in medical applications. A radionuclide generator creates this radionuclide. This table shows the radionuclides produced by radionuclide generators. This is parent radionuclide, and this is the daughter radionuclide. The half-life of the parent radionuclide is much larger than that of parent daughter radionuclides. So this radionuclide generates, we can see the same behavior. So RB has a half-life of 7.5 hours, but the half-life of KR is just 30 seconds. Okay. So the difference is very large. And G68 is half-life is 270 hours, but the daughter nuclide GA68 is just 1 hour. Okay. And SR82 its half-life is 25 days, but daughter nuclide RB82 has just a very short half-life of 75 seconds. And the column at which the parent nuclide is attached is the alumina in this radionuclide generator, and this nuclear generator is this one, and this alumina, and here also alumina, and that is the chemicals or fluid to separate the daughter radionuclides from the parent nuclide. Here saline solution is used in this generator, and in this generator we can use air. There is EDTA, and it's also use a saline solution to separate the daughter radionuclide from the parent radionuclide. For the diagnostic device SPECT, which is a single photon emission computed tomography, the radionuclide of TC99M is extensively utilized. Scientists employed radioactive iodine in the late 1930s to determine how much of a given dose of radioactive iodine was localized in the thyroid. This study was the first to use radionuclides in clinical practice. Initially, the Geiger counter was employed to detect the radioactive rays emitted by observed radioactive iodine. To detect gamma rays, scintillation material and a photomultiplier were utilized in 1948. The radioactivity of the roughly 400 locations near the neck was determined and mapped using this technology. Many radiopharmaceuticals, which is shortly nuclear medicines, based on radionuclides, were developed and used to diagnose heart, liver, kidney, and bone problems in the 1950s. TC99M was developed in the mid-1970s. This radionuclide has increased the use of radionuclides in medicine. The radionuclides produced in a nuclear reactor are transported to the hospital, resulting in a time delay before they may be used. As a result, medicinal usage of radionuclides having a short half-life was restricted. Using a TC99M generator, this problem was resolved. TC99M is a short-lived radionuclide having a half-life of only 6 hours. It emits enough gamma rays in a small dose to protect patients from radiation damage. A TC99M generator can produce TC99M. This generator is portable and consistently produces TC99M. As a result, TC99M's short half-life isn't an issue because it can be used at the same production site. Radiation detectors have seen significant advancements. Ben Kazan invented a rectilinear scanner in 1949. However, obtaining a radiation image using this rectilinear scanning method took a long time. Hall angle, that's not new, angle. Hall angle invented the gamma camera in 1957, which allowed for faster and more exact radiation measurements. We can explain this gamma camera in detail in the second section. In 1960, the first tomography image was made with this camera. PET, which is positron emission tomography, was invented in 1970, while the SPECT was introduced in 1977. These scanners produce an image of spatial distribution of radionuclides administered into the body rather than anatomical image of the body. If compared to CT or MRI, these scanners have a lower resolution. However, abnormal uptake and biodistribution of the radioactive compound introduced into the body can detect early biochemical changes due to the disease. As a result, these scanners enable early diagnosis before the disease alters the tissue morphology, which can be recognized by CT or MRI. In diagnostic nuclear medicine, TC99M has become the most extensively utilized radionuclide. It is used in about 80% of SPECT imaging procedures. Technetium-99, is a TC, is radioactive metal with a molecular symbol TC99 and a silver gray color. It can be found in very small amounts in Earth's crust. As a result, it is mostly manufactured artificially. Segre and Berio were the first to find it in 1937. Seaborg and Segre, on the other hand, discovered TC99M, which is a metastable state of TC99 in the same year. While TC99 has half-life of 212,000 years, TC99M has half-life of only 6 hours. The figure depicts the decay scheme for TC99M. A nuclear reactor produces radioactive 99 M, molybdenum-99, this one, by emitting beta particle, about 86% of molybdenum-99 decays to Tc-99m. Okay, so beta decay. Then, by emitting gamma rays, this gamma rays, Tc-99m decay to Tc-99. Finally, Tc-99 decays to Ru-99, a stable nuclide with a half-life of 212,000 years by emitting beta particle. So we can use these gamma rays to take imaging. To minimize radiation damage to the body, radionuclides for medical applications should have a short half-life. As a result, Tc-99m is appropriate for clinical application due to its short half-life of 6 hours. When radionuclides are generated in a nuclear reactor located many hours distant from the hospital, however, the radionuclides with a short half-life decay almost totally to their stable nuclides by the time they arrive at the hospital. This difficulty is solved by radionuclide generators. The radionuclide with a long half-life decays to the radionuclide with a short half-life in the radionuclide generator. The radionuclide with a long half-life is referred to as parent radionuclides, whereas the radionuclide with a short half-life is called as the daughter radionuclides. Okay. If the daughter radionuclide produced by the parent radionuclide is chemically or physically separated from the parent radionuclide, the daughter radionuclide can be obtained continuously until the parent radionuclide ceases producing it in an unusable amount. Molybdenum-99 and Tc-99m are the parent and the daughter radionuclide in the Tc-99m generator, respectively. So molybdenum-99 is the parent radionuclide, and Tc-99m is the daughter radionuclide. Molybdenum-99 atoms are chemically adsorbed to the alumina column in a Tc-99m generator. So this is alumina column, and molybdenum-99 is chemically adsorbed onto this column. By washing the alumina column with a saline solution, the Tc-99m atoms generated by decay of molybdenum-99 can be chemically separated from molybdenum-99. The Tc-99m atoms washed out of the column are stored in the bio as TCO4M, which is then used to make radio or pharmaceutical. So, small letter. After washing out the column for 23 hours, the number of TCAM atoms reaches its maximum value. We can see this in the next slide. We can now obtain TC99M by washing out the column once more. When the available amount of TC99M becomes too small to be practical, we must return the column to the company and have it exchanged. This is about a week's supply of time. This figure shows the decay of the molybdenum-99 and production of the TC99M. This is some compound decay, so we can obtain this relationship, but we cannot explain how this equation is obtained in detail. It's too complex, so we will not discuss it further. By using compound decay, we use this relationship. Here, ND represents number of total radionuclides at a certain time t, and MP0 represents the number of parent nuclide at t equals 0, initial number of parent nuclides, and lambda p is decay constant of parent nuclide. Lambda d is the decay constant of total nuclide. So we can obtain the maximum time at which the production of the TC99M become maximum, which can be obtained by taking derivative of this number of total nuclides with respect to time, and this putting this derivative putting to 0, then we can get the time at which the production of this radionuclide is maximum. So we just taking derivative of this equation, we can get this relationship, and we can get the maximum time of maximum decay rate. Putting the number lambda p and lambda d, we can obtain the 23 hours. So this means that the production of the TC99M has its maximum value at 23 hours. It's about a day. So if we wait a day, then we can have the maximum TC99M. Then we can wash out. Then we can obtain TC99M for use. And one day after, we again wash out. Then we can obtain some amount of the TC99M, but the amount is decreased because the molybdenum-99 is decaying as a function of time. So after roughly 7 days, the amount of TC99M is no longer appropriate if the aluminum column is washed out every day to obtain TC99M. So after 7 days, we cannot obtain the sufficient amount of TC99M, so we have to return the column of the generator to the company and recharged. So far, we discussed how the radionuclides are produced. I mean, artificial radionuclides are produced. There are four methods to obtain the artificial radionuclides. First, we can use the cyclotron, and then we can use the nuclear reactor by using the neutron capture or neutron capture after neutron capture, so decaying after neutron capture. And finally, we can use the radionuclide generator to obtain some specific radionuclide for the SPECT.